Hi, thanks for your interest in our work. My name is Ali Safa and I'm a doctoral researcher at IMEC and the KU Leuven in Belgium. In this presentation, I will cover our work on simultaneous localization and mapping for drones using a sensor fusion approach by fusing event-based camera and radar sensors using a spiking neural network. Unlike most learning-based SLAM systems, where a neural network of some sort is trained on the dataset captured beforehand, our proposed system does not require any network pre-training and any training set acquisition. Rather, the spiking neural network is initialized randomly and continuously learn on the fly via spike timing dependent plasticity learning, in the same time as when the drone explores the environment and performs SLAM. So, as explained previously, the goal of this work is to design a simultaneous localization and mapping, or SLAM, system, fusing event-based cameras and radar sensors using spiking neural networks. Indeed, using a single modality alone, such as RGB camera, does not provide utmost robustness to environmental effects, such as lighting variation typically encountered by autonomous agents. In this work, we propose a first-of-its-kind SLAM system using event-based camera and radar. We benchmark our proposed system against prior methods and we demonstrate the robustness of the system to strong lighting variation. In this image, we can already see a picture of the drone that we used to acquire data and to perform SLAM. The drone is composed of a radar sensor, an event-based camera, and the SLAM system produces maps such as the one shown here below, where in addition to the drone path and the map of the environment that the drone visited, we can also see the obstacles in black encountered by the drone. Crucially, our learning-based SLAM system does not require any pre-training nor any training dataset acquisition. Instead, the spiking neural network used to encode the event camera data and radar data into latent feature descriptors is learned on the fly as the drone explores the environment and performs SLAM. There is therefore no pre-training of that spiking neural network. Rather, the weights of the network get continually adapted using spike timing dependent plasticity, or STDP for short, as observed in the brain. Then the feature descriptors produced by the SNN, meaning the spiking neural network, are fed to a RAD-SLAM backend, which performs loop closure detection and map correction. RAD-SLAM is indeed a popular SLAM system, closely inspired by the hippocampus of the rodent. Hence, its bio-inspired nature fits nicely with our use of bioplausible spiking neural networks and STDP learning. Now, let's dive into the architecture behind our proposed SLAM system. As explained in the introduction, we make use of both an event-based camera and a radar in this work. Event-based cameras, or also called DVS for dynamic vision sensors, are a novel type of camera which take inspiration from how the human retina works. Event-based cameras are composed of pixels that independently and asynchronously fire spikes whenever the change in light intensity of that pixel crosses a certain threshold. The spike is said to have a positive polarity if the change in lighting intensity is positive. On the contrary, if the change in light intensity is negative, the spike is assigned with a negative polarity. Compared to standard RGB cameras, event-based cameras have some advantages, such as very low latency in the microsecond range, and a very high dynamic range with a typical order of 120 dB, which makes them very robust under low lighting conditions. For illustration purposes, the video here shows the RGB and event data captured while the drone is taking off, in order to illustrate the working principle of event cameras. As you can see, the event camera produces spikes in zones where changes happen. In addition to the event-based camera, we make use of a 79 GHz radar sensor, providing detection frames at a speed of 20 frames per second. Each frame returns a number NT of detections, which indicate the position of an obstacle at position XY on the range azimuth map with regard to the drone origin. The radar also provides the radial Doppler velocity of each detection, VD, in this slide. The plot on the right shows a detection frame captured when the drone was flying in between the storage aisles, shown here. Two sets of detections can be remarked, which corresponds to the left and right storage aisle surrounding the drone. Now that we review the working principle of each sensor used in its work, let's turn our attention to the working principles of spiking neural network and spike timing dependent plasticity learning. Spiking neural networks are bioplausible neural networks, closely mimicking the neural ensemble behavior in the cortex. They are built in a similar fashion as artificial neural networks, but differ in their use of event-driven spiking neurons. Spiking neurons, such as the popular leaky integrate and fire neuron model that we use in this work, works as follows. Given an input current G in, resulting by the inner product between the neuron weights W and its spiking input vector S, the neuron integrates the input current J into its membrane potential V with a leakage speed set by the membrane time constant, tau m. Then, when the membrane potential crosses a certain threshold mu, the neuron emits a spike. This is also shown schematically in the graph here. You can see the input spike trains coming in, the membrane potential gradually integrating these input spikes with a certain leakage, and when the membrane potential crosses the threshold mu, an output spike is emitted. The use of spiking neurons has recently gained much attention for building ultra-low power processing devices that consume dynamic energy only when spikes are emitted. In order to train spiking neural networks in a bioplausible way, we make use of spike timing dependent plasticity, or STDP for short. STDP is a local Hebbian learning rule observed in the brain, which works as follows. Given a spiking neuron receiving a presynaptic spike train as input and emitting a postsynaptic spike train as output, STDP modifies the weights associated to the input spike trains according to the time difference between the output spike and the input spike. If the time difference, tau here, is positive, it means that the output and the input spikes are positively correlated because the output spike was fired after receiving the input spikes. And so the weight associated to that input spike is increased by an amount given by the STDP kernel here. Conversely, if the time difference between an output spike and an input spike is negative, the weight is decreased. Potentiation and depression of the weight is done according to the double exponential STDP kernel, which has 4 parameters. The potentiation and depression amplitudes, AP and AN, and the decay constants for potentiation and depression, tau P and tau N, corresponding to each case about the sign of the time difference between a postsynaptic spike and a presynaptic spike. In this work, we make use of the following baseline spiking neural network architecture, which is used to encode the input sensory observation S into a lower dimensional latent code C that is then fed to the SLAM backend. The network is composed of two fully connected layers of spiking neurons. First, a coding layer in green here, which is composed of an input weight matrix and a recurrent weight matrix W. Second, there is a so-called error layer, which takes as input the output of the coding layer through the weights psi and feeds its input back into the coding layer. All weights learn independently of each other via spike time independent plasticity learning in an online continual manner. It can be shown that this network architecture implicitly solves the following unsupervised learning problem. Given a spiking input vector S, the network infers an output code C and learns at the same time a set of weights noted phi here, such that the reprojection error between the output C and the input S is minimized in this L2 norm loss. This is akin to an autoencoder. The other terms here in the energy function enforce sparsity of the output through the L1 regularization of the output, and also have some weight decays associated to the learning of the weights in order to combat overfitting through the two hyperparameters setting their respective strength, lambda 1 and lambda 2. In this slide, we show the proposed sensor fusion architecture using the spiking neural network baseline described in the previous slide. Each sensor is processed by its own SNN-STDP network, shown as green boxes in the schematic here. Each green box thus represents an instance of the baseline spiking neural network that we saw in the previous slide. Regarding the event-based camera, positive and negative spikes are processed by two distinct SNN-STDP networks. The radar detection map are seen as maps of binary events, which is akin to spikes, and are therefore fed to their own SNN-STDP network directly. Before being fed to each network, the 2D sensory data are flattened as 1D spiking vectors. Crucially, as the data is being fed into the networks, the STDP learning rule continually tunes the network weights in an online manner. Then, the output spikes from each SNN-STDP unit are concatenated together as a single spiking output. After that, we perform local averaging of the spike trains using an averaging window of size delta t. After this step, the spiking output is converted to a vector of continuous values, of spiking rates this time. Then, those rate vectors, after averaging, undergo online standard scaling, where each component is subtracted by its mean value, ML, and divided by its standard deviation. Here. The mean and standard deviations are aggregated online as the system receives data in. This standard scaling helps providing statistical invariance properties useful during the template matching between different latent codes when the RADSLAM backend is performing loop closure detection. Finally, the standardized latent codes are fed to the RADSLAM backend and are assigned to their respective drone poses derived by RadSlam using the provided inertial odometry information, meaning the drone heading velocity and yaw angle rotation speed. Now we will cover how odometry is provided to the RadSlam backend. We will also cover how the various obstacles and walls are modeled in our system. Since the use of accelerometer data can be noisy due to the drone vibrations, we propose an odometry strategy using the radar sensor instead of the accelerometer to acquire the drone heading speed. Indeed, the radar already provides the radial velocity of each detection relative to the drone. Hence, the drone velocity can be derived from the observed obstacle velocities as follows. Given a single detection with coordinate xy and radial velocity vd, the heading velocity is derived as minus vd over the cosine of theta, where theta is the angle between the obstacle and the y-axis in the drone coordinate system. In practice, since multiple detections are available for each radar frame, we compute the drone heading velocity as the median value of all the velocities derived from each single obstacle. Using the median value is indeed a sound choice due to its robustness to outliers. The algorithm given here shows how the drone heading velocity is computed for each radar detection frame. As you can see, it loops over all the single detections in that frame, computes each single estimation of the drone velocity, and then returns the median value of it. Finally, the drone yaw angle rotation speed is provided by the onboard gyroscope. In addition to odometry, the radar can be used as a direct and robust method for reconstructing the walls and other obstacles present in the environment. At each time step k, the radar detections can be added on top of the previous ones corresponding to the previous time steps in order to gradually reconstruct the shape of the obstacles. Since the radar detections are obtained in the coordinate system of the drone, they must be projected in the global coordinate system of the map produced by the SLAM backend. This can be done by rotating the detections xd, yd according to the drone yaw angle psi and translating the detection by the drone position capital X and capital Y with regard to its starting position and starting angle. These obstacles are added as an additional side information to each pose registered by the SLAM backend. Therefore, each time a loop closure is detected, the SLAM backend not only refines the past drone poses, meaning psi and the position xy, but also recorrects the obstacle coordinates by applying rotation and translation again to the detection coordinates small x, small y. The graph on the right shows the result of this process, where the black dots correspond to the aggregated detections along the drone trajectory. Now that all the components making our system have been covered, the next slides will overview and discuss our experimental results. In order to conduct our experiments, we collected joint event camera and radar data by flying the drone in an indoor warehouse environment composed of storage aisles. We collected data under 3 flights. The first flight follows the blue path on the left image here, where the drone performs loops around the first aisle here in blue. The second flight sequence is obtained as a combination of all the 3 paths shown here, meaning the blue, the red, and the green path. Crucially, we also acquire a third flight sequence following the blue and the red path, while at the same time randomly turning lights on and off in order to create severe lighting variations in the environment. In addition, ground truth positioning of the drone is obtained using an ultra-wideband, or UWB, beacon placed on the drone, as you can see here. This environment contains a high amount of visual ambiguities between the various scenes, as can be seen here between those images, making the disambiguation of the drone location challenging. As a first demonstration of our system, this video shows a proposed SLAM architecture in action. The result of the localization and mapping will be shown in the bottom left graph, where the red cross here indicates the drone position. The graph right next to it will show the raw odometry result of our proposed radar-gyroscope method, which is fed to the SLAM backend in order to produce the result shown in the bottom left graph. On top, the RGB output is shown only for information purpose and not used by the system itself. As you will see here, lights will be turned on and off in order to demonstrate the robustness of the system against strong lighting variation. Next, the event camera data and radar detections are shown in the two right plots here. Finally, the bottom right plot shows a subset of the weights of the spiking neural network. As you will see, the weights are first initialized randomly and will evolve through time as the drone explores the environment. Therefore, there has been no pre-training of this spiking neural network and no prior acquisition of a training set. Rather, the drone performs SLAM while learning on the fly at the same time through spike timing dependent plasticity in a continual online manner. So here is the drone SLAM system in action. As you can see here, the light was turned off, now turned on again, and the system is indeed robust to these low lighting variations. Also, we can see the weights that are now learning environment-related features, even though they started as random weights initially. Gradually, the map of the environment is built and the obstacles are aggregated in black. In this slide, we compare the result of our approach against a number of RGB-based solutions, such as the baseline RedSLAM architecture. We also compare our approach against the latent SLAM architecture, which is a state-of-the-art learning-based SLAM system built around variational autoencoders, and which uses the RedSLAM as its SLAM backend, like in our work. Finally, we also compare our results against the popular ARB feature matching technique used in many SLAM systems. The various graphs shown in this slide compare the results obtained by each technique. We also perform ablation studies of the event camera and radar sensors in order to study the impact of each modality to the SLAM results. Visually, it can be already seen that our system outperforms the other architecture under strong lighting variation in the sequence shown here, corresponding to the flight sequence 3 when we were turning on and off the lighting in the room at random. In addition to the visual results shown in the previous slide, we quantitatively assess the performance of each method by computing the mean absolute error, or MAE, of both the drone localization and the produced map. The error is computed against the ground truth acquired using the ultra-wideband beacon placed on the drone. We also perform ablation studies of each sensing modality in order to assess the effect of the sensor fusion approach. Compared to the previously proposed RGB-based solutions reported in this table, our proposed system outperforms both the original RAD-SLAM and the latent SLAM, which makes use of an 11-layer deep neural network trained offline. In addition, our system either outperforms or reaches close mean absolute error compared to ORB features used with RGB. This is remarkable given the small size of our SNN-STDP network. So our spiking neural networks are equivalent to a one hidden layer network in terms of complexity, in contrast to the 11 layers used in the latent SLAM setup. Also, another advantage of our system is the fact that our network is not pre-trained offline, as in latent SLAM, but is rather initialized randomly and learns features from the input data on the fly via unsupervised continual STDP adaptation. Therefore, it does not require the acquisition of training sets before drone deployment. Finally, the fact that our system does not use RGB, as in most SLAMs, but solely relies on event camera and radar data, allows the system to work properly under low lighting conditions as well. In conclusion, this work has presented a first-of-its-kind bio-inspired SLAM system fusing event camera data and radar sensing using spiking neural networks. Crucially, unlike most learning-based SLAM systems, where a deep neural network is trained offline using a training set captured beforehand, our proposed system does not require any pre-training and relies on the continual adaptation of the network weights via spike timing-dependent plasticity as the drone explores the environment. Finally, we saw that our system reports competitive performance compared to state-of-the-art RGB solutions, while enabling robust navigation and obstacle modeling even under low lighting conditions. Thank you very much for your attention.